All right, here's a third example of how to use the kinematic equations for rising and falling motion. An example of volleyball. So on the volleyball court, a setter launches a ball straight up in the air for another player to hit. The setter gives the ball an initial vertical velocity of positive 6 meters per second, and then 4 questions about that. So here's my little picture of the situation, right? Somebody's setting a volleyball straight up at 6 meters per second, and it looks like I left off the little S there. By the way, if it's being set straight up, then the ball would go straight up and down, right? But that's not quite how I drew it here. I drew it kind of moving over to the right. And I did that just to space out the drawing. So you would have to imagine that in real life, the dots of the position of the ball would more stack on top of each other vertically. Okay, so let's take a look at the first example. The first question, what's the volleyball's velocity 0.75 seconds after it's launched? Okay, so we're going to be looking at some moment like maybe it could be this moment here, or it could be maybe up in any one of these three. How fast is it going 0.75 seconds after it's launched? And by the way, we would know if at this moment, 0.75 seconds, the ball is in its rising motion or in its falling motion based on whether the velocity that we get is a positive or a negative number. So let's investigate that. We're going to use equation 2. The final velocity is just the initial velocity plus the acceleration times the time. The initial velocity is 6 meters per second, right? We have that here. And then we're going to just add free fall acceleration. Of course, it's negative because it's downward. And then we have the time, 0.75 seconds. So the ball would be going negative 1.35 meters per second. So this means that the ball is starting to fall back down, right? It's a negative number, so we're in the downward direction. So that's got to be, here or here along the path. Let's try question B. How high does the ball go from where it's launched? In other words, what is its maximum height? Okay, so now the question is more like this. This is where the ball is being launched, but how high up to the top is this, right? So we're talking about delta y. How high does it go? Well, we need to use a clue embedded in this question. Sometimes I call them hidden givens, and it's this. At the maximum height, we know something is true of the ball. And what is true of the ball at its maximum height? Well, it's that the velocity is going to be 0, right? That's something that you develop with practice as you work on these kinds of problems. So what we're going to do is we're going to sort of pause the analysis here at the peak, okay? We're going to stop at the peak and we're going to start here. We're just going to look at the rising motion of the ball. And you say, can you do that? And I would say, for sure. In fact, I did another video called Choosing Initial and Final Moments in Linear Motion. And so that's the skill here, right? Is when do I want to start my analysis? When do I want to stop my analysis? And I'm going to start here at the place where the setter sets the ball, and I'm going to stop here at the peak. Okay, those are my initial and final moments. So let's use equation 3. V final squared is V initial squared plus 2A delta y, right? Delta y because I'm looking at the vertical direction. And at the final moment, which is at the peak, my velocity is 0, okay? At the initial moment, which is right after the ball leaves the setter's hands, the velocity is 6 meters per second. Still accelerating at free fall acceleration, and then delta y is my unknown, right? So I'm going to do 6 squared, bring that over to the left side. So then I'd have negative 36 meters squared per second squared equals negative 19.6 meters per second squared times delta y. I would divide both sides by negative 19.6, and I would get that delta y is 1.84 meters. So that is how high above the setter's hands the ball goes at its maximum height. Let's try the next question. question. Question C. If the hitter totally misses the ball, right, and it starts to come back down, what will be the ball's hang time when it returns to its original position? So now we're talking about down here, if the ball comes back, it goes through the peak and falls all the way back down to where it started. What's the time here, right? How much time would it take to come back to where it was launched from? So there's another hidden given here, okay? And it's this. We know that the ball was launched with an initial vertical velocity of 6 meters per second, right? The setter pushed the ball up at 6 meters per second. So if the ball is rising, right, it's going through this position, it goes through the peak, it starts to come back down, and it now reaches the same height to where it started, do we know what this final velocity is? And the answer is yes. If the motion is completely symmetrical like this, then we can say that the final velocity is going to be the same as it started, but negative, right? 6 meters per second. So that's the hidden given in this situation. When the ball comes back down, the velocity is just the same, but in the negative direction. So we're going to solve for time. We're going to figure out how much time it takes for the ball's velocity to go from positive 6 to negative 6. And that sounds like an equation 2 opportunity. Okay, the final velocity is negative 6. The initial velocity is positive 6, right? Accelerating the whole time at 9.8 meters per second squared. Okay, so I'd subtract 6 from both sides. I would divide both sides by negative 9.8, and the time is going to be 1.22 seconds. All right, final question. With how much velocity would the setter need to push the ball in order for it to go 10 meters above her set point? Okay, so now the question is, all right, let's say that the initial velocity was unknown, but we know that the ball is going to go 10 meters high from where it's being set. Okay, how much velocity is required for that? So again, we know something is going to be true about the ball at its max height, right? We're going to just isolate the rising motion of this ball. So when the ball reaches 10 meters above her set point, it's at its max height. And again, as I stated before, right, at the max height, the velocity is going to be 0. Okay, so I'm going to isolate just the moment from when it's launched to when it reaches the peak. I'm just going to look at the rising moment. Those are going to be my initial and final times, and I'm going to go to equation 3. Okay, the final velocity is going to be 0. The initial velocity is unknown. The acceleration is negative 9.8. And delta y is 10 meters, okay? This obviously goes away. I'm going to pull over, so then I'll have negative 19.6 meters per second squared is, times 10, sorry, negative 196. And that's going to be meters squared per second squared is going to be equal to V initial squared. And so V initial is just the square root of that. 14 meters per second. Okay. And now you might say, isn't it plus or minus 14? Because, my mistake, this is a positive number, right? You might say, isn't it plus or minus 14? And it is, but we know that the initial moment is over here. So we need to use the positive root of that. So if the ball is pushed up at 14 meters per second, then it will reach a maximum height of 10 meters.